All right. Good morning, everybody. Welcome back. So for today, let's pick up where we left on Monday. So let's see here the last thing we talked about. Okay, so the last thing I talked with you about on Monday was polarity. Every time we have a covalent bond, that means we are sharing electrons. Ideally, both elements would share equally the electrons involved in the chemical bond. However, because some elements are more electronegative than others, those more electronegative elements will tend to pull the electrons close to itself compared with the other elements involved in the chemical bond. The order for electronegativity, the most electronegative element is fluorine, and then that moves on from left to right, and hydrogen will be the least electronegative element in a covalent bonding. And then let me actually switch to the other screen. Okay, and then I showed you how to represent the electron density for the element that has low electron density. So that's going to be a delta plus, and the element with high electron density is going to be the delta minus, okay? So in this case, in this example here, we have the covalent bond between carbon and oxygen. Oxygen is more electronegative than carbon, therefore it will pull the pair of electrons close to itself compared with carbon. That results in an accumulation of the electrons close to the oxygen and a deficiency of electrons close to the carbon. Therefore, we are polarizing the covalent bond, and we indicate that there is a polarization by the vector in green, pointing from the carbon towards the oxygen. And therefore, here we have a polar covalent bond. Okay, so we can analyze bond by bond in a compound and determine if the bond is polar or non-polar. And then we can see the compound as a whole and determine if the whole compound is polar or not. So let's recap here the CO2 example. CO2 is a linear molecule, and we are going to tackle that in the next chapter. We know that the carbon-oxygen bond is polar, and we also know that the vector points from the carbon towards the oxygen. Okay, so representing here the vector for the carbon-oxygen bond on the right side, and we have the same thing for carbon oxygen to the left side. Okay, so the polarity of the carbon oxygen on the left points from the carbon to the oxygen. To figure out if the whole compound is polar or non-polar, we have to add all the vectors in the compound. So here for CO2, we have two vectors, one pointing to the right, another one pointing to the left with the same magnitude. Therefore, the resulting vector is going to be equals to 0, okay? Pulling to the right with the same intensity as the pull to the left, those vectors will cancel. Resulting vector is equals to 0. Therefore, the CO2 compound as a whole is a non-polar compound. Okay, I just want to introduce this concept. We are going to tackle it again in the next chapter, and that's going to be a more refined approach. For now, we just need to know when a covalent bond is polar or non-polar. And if you are talking about the whole compound, we have to consider all the vectors that are contributing to the polar covalent bonds. Okay, very good. I will talk about solubility in the next chapter, but the rule of thumb is that polar compounds, they will dissolve polar compounds, and non-polar compounds will dissolve non-polar compounds. Okay, so a polar compound will not be capable of dissolving a non-polar compound. Okay? Similar with similar, if we have two opposites, we have no solubility. Okay, and again, I will cover this with more details during the next chapter. Then we can talk about geometry as well. Okay, so that's the important point for today. We are going to talk about formal charge. Okay, formal charge is the property that will tell you if a structure of a covalent compound is stable or not. So formal charge is going to be very important when we have more than one possibility to connect the atoms. And one of those possibilities are going to be the most stable, and the formal charge is the number that's going to tell us which structure is the most stable. In the calculation of formal charge, the atoms are considered to have the same electronegativity. Therefore, the electrons are equally shared. Formal charge will give you an idea about if an atom in a covalent bond is having the electrons close to itself, or if the electrons are being equally shared. To calculate the formal charge, we are going to use this formula. Formal charge is equal to the number of valence electrons minus half of the number of bonding electrons minus the non-bonding electrons, or lone pairs. And we are going to follow three rules to figure out if a compound is stable or not. First one, the most stable structure has the lowest formal charges on the atoms. Stable structures, they usually have formal charge equals to 0 for all the atoms. Second point here, double or triple charges are not stable. If there are negative charges, the lowest charge has to be in the most electronegative atom. So what we are looking here is for ideal sharing of electrons, therefore formal charge equals to 0. If we have a negative charge, it must be located in the most electronegative atom, because that's the atom that has a stronger pull towards the electrons. When we are calculating the formal charge in a covalent compound, we are going to determine the formal charge for every atom in the structure. So let's start here with the PCl3 example. So everything starts with the Lewis structure. So I'm going to go fast here because we already tackled that. So we have phosphorus as the central atom connected to 3 atoms of chlorine. And then we start filling up the octet with the leftover electrons. And for this structure, we have a lone pair on the phosphorus as well. Okay. So the calculation of formal charge is going to involve the formal charge of all the elements present in the structure. So let's start here with the phosphorus. So let's, calculate the formal charge for the phosphorus atom. So I'm going to represent that as FCP. And then let me repeat the formula here on the top. So we have here valence electrons minus half of the bonding electrons minus non-bonding electrons. Okay, so let's determine the formal charge for phosphorus. Valence electrons means the number of valence electrons for the atom. How many valence electrons phosphorus has? Okay, so phosphorus belongs to the group 15. Therefore, phosphorus started with 5 valence electrons. In this compound, phosphorus is going to be combined with chlorine. Therefore, we have bonding electrons. Now, what we are going to do is to count how many electrons are being used to bond phosphorus with all the chlorines, okay? So each single bond counts as 2 electrons. So we have 2, 4, and 6. Therefore, phosphorus is using 6 electrons to make all the chemical bonds, and that's going to be the number of bonding electrons. Remember that each covalent bond counts as 2 electrons if they are single bonds. After the phosphorus bonded to all the chlorines, is there leftover electrons for this atom? So in other words, is there any lone pairs or non-bonding electrons on the phosphorus? And the answer is yes. So those are the lone pairs or non-bonding electrons. And for phosphorus, we have just 2. So we are going to subtract 2 electrons. Therefore, the formal charge for phosphorus is going to be 5 minus 3 minus 2, which is equals to 0. So that's the ideal situation when you have a covalent compound. Formal charge equal to 0. So far, this compound is stable. Now we have to figure out the formal charge for chlorine. Okay, so once you got the formal charge, the way to represent that is a number on the top right corner between parentheses. Okay, so let's clean up this structure a little bit. So we have here PCl3. And we determined that the formal charge for phosphorus is 0. So let's put that in between parentheses on the top right corner. Okay, so now let's determine the formal charge for the other atom involved in the formation of this compound. So now we are going to look at the chlorine. Technically, we have to determine the formal charge for all the chlorine atoms. However, all of them are making a single bond, and all of them have 3 lone pairs, so they are going to be all equivalent. Therefore, we are going to determine just once the formal charge for the chlorine atom in the compound PCl3. And here, the order, the strategy is the same. Let's first start with the number of valence electrons for this element. Okay. Chlorine belongs to the group 17. Therefore, it has 7 valence electrons. So that's how chlorine started. From these 7 electrons that chlorine started with, we are going to subtract half of the number of bonding electrons. Again here, chlorine is making 1 single bond with the phosphorus. So I'm just looking at 1 PCl bond here, okay? Each single bond needs 2 electrons. So it's going to be half of 2. After the chemical bond, is there any leftover electrons for this atom in the form of lone pairs? So those are the non-bonding electrons. And for chlorine, we have 2, 4, 6 non-bonding electrons. Therefore, the formal charge for chlorine is going to be 7 minus half of 2, which is 1 minus 6. And that's going to give us a formal charge equal to 0. And we are going to represent that in between parentheses on the top right corner. Because all the chlorine atoms are equivalent, they are doing the same kind of bond and have the same number of valence electrons, the formal charge for all the chlorine atoms is going to be 0 in this structure. Okay, so the formal charge gives us an idea of how many electrons the element started with before bonding, and how many electrons were left after bonding and non-bonding electrons. Ideally, the formal charge has to be 0 for all the elements in a covalent compound to render stability for this element. The formal charge 0 means that the electrons are being perfectly shared in the structure. Therefore, the sum of formal charges for the compound PCl3 is 0. That means this compound is stable. To determine the stability, we will always follow these 3 points that I'm showing here at the bottom of the slide. First one, most stable structure has the lowest formal charges on the atoms, meaning formal charges 0. Double or triple charges are not stable, either positive or negative. And if there is a negative charge, this charge has to be located in the most electronegative atom, because those are the atoms that pull the electrons the strongest. Okay. Okay, so now let me give you an example where 2 or more structures are possible, and we have to decide which one is going to be the most stable. And to do that, we are going to use the formal charges to guide us. So let's take a look at the case of the CO2 molecule. So let me quickly sketch here. So CO2. Let's count the number of valence electrons for this compound. That's going to be 1 times 4 electrons from the carbon, plus 2 times 6 electrons from the oxygen. Therefore, we have a total of 16 electrons to be shared among the atoms. Let's use the Clark's rule to help us figure out if we have single bonds, double bonds, or triple bonds. So we are going to compare X, which is 6 times N plus 2. So remember here, for X, we are only counting the non-hydrogen atoms. So we have 6 times 3 plus 2, which is 20. And then now we compare X with the total number of valence electrons. So we are going to subtract X from the total number of electrons, and that will give us 4. Okay, when we have 4, according to the Clark's rule, we may have two possible answers for this problem. Either, two double bonds or one triple bond. So this is one case that the Clark's rule will not give you a straight answer. It will give you two options, and you have to decide which one is going to be the most stable. So which of the options is the most probable? To figure out which option is the most probable, we are going to calculate the formal charge for both options. All right, so let's start with the option that tells us that we have one triple bond. For the option that tells us that we have one triple bond, we are going to have carbon as the central atom, a triple bond connecting carbon with one of the oxygens, and therefore a single bond connecting the carbon to the other oxygen. To connect the atoms, we used 2, 4, 6, 8 electrons. Therefore, we have a leftover of 8 electrons. We are going to use those to fill up the octet of the 2 oxygen atoms, okay? And here we have the octet completed for all the atoms in the structure. So now let's calculate the formal charge for all the atoms in the structure. If an atom is equivalent to another one, then just calculate it once. When I say equivalent, means that the atoms are making the same kind of bond and they have the same number of valence electrons. Starting here with carbon, formal charge for carbon, we are going to take into account the number of valence electrons for this element, which is 4, minus half of the number of bonding electrons. For each covalent bond, we used 2 electrons. Therefore, carbon has 2, 4, 6, and 8. Okay, so each trace counts as 2 electrons being used. Because carbon has 4 traces around it, we are going to use 8 electrons. Minus the number of non-bonding electrons on the carbon, which is 0. Therefore, the formal charge for carbon in this structure is 0. Okay, so far, carbon is good because it has formal charge 0. So now let's take a look on the oxygen on the right side of the structure. So I'm going to call this oxygen number 1, just to differentiate from the other oxygen. Formal charge for oxygen number 1, same thing. Number of valence electrons for the oxygen is 6, minus half of the bonding electrons. Each trace counts as 2 electrons. We have 3 traces connecting carbon to oxygen, therefore 6 electrons, minus the number of non-bonding electrons for the oxygen number 1, right here, is 2 electrons. Therefore, we are going to get a formal charge for oxygen number 1. 6 minus 3 is 3, minus 2 is plus 1, or 1 plus. Okay, so we got a formal charge that is different from 0, and even worse, is positive, located on the most electronegative element in the structure. So that tells us that something is wrong with this structure. I'm going to calculate the formal charge of the other oxygen just to confirm that something's wrong, and then we will confirm that this structure is not the best, and we have to move on to the second option. So let's just calculate the formal charge for oxygen number 2, just to confirm that we have problems here. So number of valence electrons is 6. Half of the bonding electrons, which is 2 in this case, because just one single bond, minus number of valence electrons is 6 for oxygen number 2. We get here a formal charge of minus 1 or 1 minus. Okay, so therefore we have charges that are different from 0, 1 minus, 1 plus, and even worse than that, the positive charge is located on the oxygen, which is the most electronegative. And because of that, that means this structure is not stable. Okay, there was another option for the CO2 structure, which uses 2 double bonds. So let's take a look at this option and see if it will render a more stable compound. 2 double bonds. Now with 2 double bonds, we still have carbon in the center, but this time 2 double bonds for both oxygens. So to connect the atoms, again, we spent 8 electrons. There are 8 leftover electrons that we are going to use to fill up the octet of the oxygen atoms. Okay, so see now that the 2 carbon-oxygen bonds are equivalent, meaning it's a double bond for both, and both oxygens have 4 non-bonding or lone pair electrons. So now let's calculate again the formal charge for all the atoms involved and see if we get a better situation than the first one. Starting here with carbon. So again, number of valence electrons minus half of the bonding electrons. Each trace counts as 2. We have 4 traces, therefore 8 electrons, minus non-bonding pairs, which is 0 for carbon. Therefore, for the atom of carbon, we have a formal charge, again, equals to 0. So carbon is still good. The problem here was the oxygen. So let's see if we solved this problem for the oxygen, making 2 double bonds instead of a triple and a single. Now let's calculate the formal charge for the oxygen. Again, number of valence electrons, 6, minus half of the number of bonding electrons. Each trace counts as 2. For carbon-oxygen bond, each carbon-oxygen bond, we have 4 bonding electrons. Minus the number of non-bonding electrons for the oxygen atom, which is 4 as well. 6 minus 2 is 4, minus 4 is 0. Therefore, now the formal charge for both oxygens is 0. Now look at that. The structure with 2 double bonds has all the formal charges equal to 0, compared with the structure with 1 triple bond where we had a positive charge on the oxygen. This structure with 2 double bonds is the most stable. Okay, so when we are comparing the formal charges of compounds with different possibilities for the structure, we have always a comparison within the possibilities. In this case, for CO2 in specific, the structure that has 2 double bonds is the most stable compared with the structure with 1 triple bond and 1 single bond. And the reason for that is that 2 double bonds yield formal charge 0 for all the elements. We are always going to look for formal charges 0 for all the elements. Double and triple charges are not stable. If we cannot get 0 formal charges for all the atoms and we end up with a negative charge, this negative charge has to be located in the most electronegative atom in the compound. Okay, so one trick to determine if you got the formal charges correct, if you add all the formal charges for all the elements in the structure, it has to match the charge of the compound. CO2 is neutral. Therefore, if we add up all the formal charges, that has to result in 0. That's true for the second option, 0 plus 0 plus 0. And it's true for the first option, -1 plus 0 plus 1, that yields a total charge of 0 that matches the charge of the compound. Okay, so calculating the formal charge will give you a guide to determine if the structure that you got is stable or not. Follow those three rules here, and that will cover all the compounds that we are going to analyze. The Clark's rule is very, very useful, but sometimes it offers you two options and you have to decide between the two, and sometimes it fails. And using the formal charge calculation will tell us if the structure is stable or not. Okay, so with that being said, I will finish earlier today, and I think that's enough for you to study. And on Friday, we will have regular lecture, okay? So be here again for this coming Friday. And we will move on to the next chapter, which will deal with molecular geometry. Okay, so have a good day, and I will see you on Friday. Bye-bye.
Thank you.
Bye. Thank you.
Thanks, Professor.
Thank you. Have a nice day.
Bye-bye.